example in the domain of autonomous vehicles. So yesterday we studied the idea of open loop and closed loop controls systems and the elements of open loop and closed loop control system and a simple block diagram and various components of control system, right from sensor to the controller. So with this knowledge of control system, we'll proceed further. We'll proceed further to know the different elements of closed loop control. So we have discussed about comparison element, we have discussed about control element, correction element, process element, which is nothing but plant, and measuring element or measurement element, which is nothing but sensor. So the control systems can be again classified as single input, single output system or SISO systems and multivariable control system, which is nothing but multi-input, multi-output system. So we have seen an example of water level maintaining in a tank. So here we understood there was only one input and one output. Okay, some students are messaging me the assignment. No need to message like this. I repeat, please do not message me to my personal number. For you, it is one contact number. For me, I have to handle 70 different heads. So it is difficult for me. WhatsApp is not an official contact. Either you try to mail or we can submit it to Ganesh. In turn, he will submit it to me through mail. So I'll make it clear. Please don't WhatsApp me. Okay. Fine. We are discussing about single input, single output systems and multi-input, multi-output system. So considering the example of water level maintaining in a tank, given a reference input and there is an input wall and there is an output wall. So we have only an input parameter, which is nothing but the volume of water coming in. So it is a single input. Okay. And the water going out, the volume of the water going out of the tank is another parameter, which is nothing but single output. So we can call it as single input, single output system. So a single input, single output system can be either open loop or closed loop. It depends. Okay. But the thing is there exists only one input, one output. Now let us look into multi-input and multi-output or multi-variable control system. So many practical things in the real world are a multi-variable control system type, which will have, which we can represent using this block diagram. So we have different inputs. There are three arrow marks indicating at the input side, which is nothing but multiple inputs. So let us take an example of say riding bicycle or bicycle as a system. Then we have more than one inputs to be given, okay, to maintain or control the bicycle. So one is the pedaling force, another one is the direction, then another one is nothing but applying brakes whenever necessary. Okay, so here this applying pedaling force and giving the desired direction are basically like instantaneous desired inputs or set points, we can say. I mean, the desired direction keeps on changing as you go on moving towards your destination or target. So they are also called as set point inputs, but to be precise, we can call it as instantaneous set points or instantaneous reference points. So which will be fed to the pedaling force will be fed to the rear wheel, then direction for the front wheel. So in turn, you can ride the bicycle properly to reach your destination. So looking at this block diagram, here the involvement of controller is through human being. Okay, it's through human being. So process is again bicycle measurement is like what you are sensing through your eyes. So your eyes will sense more than one parameter. Okay, it will never like limit the measurement to one parameter. So there are multiple parameters to be sensed by your eye. So measurement parameter will take more than one inputs. So for example, you have to look at the vehicles moving around you. You have to look at the traffic signal. You have to look at the condition of road. Okay. And apart from that, you need to look at the speed with which vehicles are moving around you. Okay. So that's why it is very important to understand the concept of multivariable control system. And this is one such block diagram representing a multi-input, multi-output system. So next, even the output variables are also more than one. Okay. So output variables are more than one because you need to maintain, say, speed of the vehicle, you need to maintain the acceleration. Okay. You need to maintain the position of the bicycle, and you also need to maintain the. Okay, thanks for that. I hope multi-input, multi-output is clear for everyone. So next, moving on to a little deeper, what is control engineering is about. So in simple words, it is analyzing the stability of the system. I mean, what a control engineer does is analyzing the stability of the system, then analyzing the dynamic response and performance indices, then designing the controller accordingly. So let us look into a stability parameter. Stability. So stability, the more simplest word for stability is like behaving normal. Okay. So there are certain systems which are, categorized as inherently unstable system. Okay, inherently unstable system, and we need to design a controller for such systems to maintain stability. So when we analyze stability of systems or such systems, what we are going to do is the extent of instability or the extent up to which the system will be stable. So I said there are some systems which are inherently unstable. So what does it mean is like, suppose consider an example of magnetically levitating ball. Okay, you have a metallic ball and you are maintaining its position in the air through the magnetic field created by a, say, electromagnetic coil. It is called as magnetically levitating ball. So if there is no field or no supply given to the electromagnetic coil, of course, you cannot control the position of the ball in the air. So what does that coil creates is that magnetic field which is sufficient enough to maintain or attract the ball from the ground in the air. You can Google it. You can Google it and see about magnetically levitating ball. So when there is no supply given to the electromagnets, there won't be any magnetic field. So you cannot maintain the position. So the metallic ball will lie on the ground. So we can categorize this as inherently unstable. Okay. So if there is no input, then we don't achieve any desired response. Okay. And another category of systems in which the system will attain to instability. Okay, the system will attain to instability after certain stability level. Okay, after certain stability level. For example, imagine you have not submitted assignment and I will start scolding you in the class. So I will shout at you for 5 minutes, 10 minutes, 15 minutes, and after 20 minutes you will get angry. And you will also start losing control because you are also a human being. And then you will behave abnormally. Yes. Okay. So up to certain point you are stable, and after certain point of time you are unstable. So that is another kind of stability with respect to system. So of course that was funny example. Let me consider another example, say bike. So imagine someone is having a KTM bike and want to have fun on highway. So you will start your bike and start increasing acceleration, and after some time you'll reach 120 kilometers per hour. Okay, that is fine. And after some time you will reach, say, 180 kilometers per hour. So how do you feel at 180 kilometers per hour? The bike will start shaking, right? And if you want to have more fun, you still increase the speed to 200 kmph. And if you encounter with any disturbance on the road, okay, any disturbance on the road in terms of, say, a hump, Okay, then the system will become unstable. So what we can term about the, I mean, what we can interpret about this system is like up to certain range of speed, the bike was stable, and after certain speed, like after the limit is crossed, the system became unstable. So we will analyze this type of stability mathematically. Suppose imagine you are a designer and customer will ask you, you design me a bike and give me the specifications. Then you need to give the stability specification also to him. Okay, by mentioning this is the speed limit up to which you can ride it safely. So how do you get that specification value or that specific value? So let me call it as a threshold of stability. It is by mathematical calculation or mathematical analysis. Okay. So what does that mathematical analysis involve? That mathematical analysis of stability will involve the parameters of the system. Okay. So the parameters of the system, one such example is mass of the bike. Okay. So you need to know the mass of the bike to calculate or evaluate the stability of the system. So that is of course obvious. So in that way, car is more stable than bike. Okay. So that is one way of analyzing stability. So that is first aspect of a control engineer. Next, second aspect comes as dynamic response. This is a very important parameter in any control system. So what is the word dynamic or dynamics means? Usually we call say dynamics of a system. Okay, the term dynamic is more related to system. So what is meant by dynamic system? We have already discussed. Let me repeat it again. Any system which responds to an input. Any system which responds to an input signal. What I mean to say input is either it is a physical signal or an electrical signal. Such systems are called as dynamic systems. So you can consider say table. Table is a dynamic system because if you apply force, it will displace. It will get displaced. So it will respond by getting displaced. So the amount of force that you are applying to that table will be responsible for displacement. So the dynamics of the table can be governed in terms of mass and the force applied and the displacement occurred. And suppose imagine if you have say a table weighing 1 kg and imagine you are applying some force of say F newtons, then there will be a displacement of d meters. And if you have another table whose mass is say around 1000 kgs, and if you are applying the same force F, will the displacement will be same? No. So displacement will be different. It may be very small, but there will be some response. So I hope you are getting that. So this is what dynamics of a system means, and the dynamic response of the system, or the word dynamic response means it is the response of the system for a given input. That's it, very simple. So I repeat once again. The dynamic response of the system means it is the response of the system for the given input. Very simple. So what we need to analyze with respect to dynamic response of the system or dynamic behavior of the system. Suppose imagine you are giving a DC input to a resistance, okay, to a resistance. So you can imagine the DC voltage input as in terms of a say sharp rise in the input value from 0 to 5 volts at particular instant of time. So if you plot the graph, I just try to imagination, there is nothing big I am doing here. Everyone is aware of DC signal. So if you imagine a DC signal, there will be a sharp rise from 0 to 5 volts at a particular instant of time. Then what happens to the current? The current in the circuit will also rise sharply as soon as you apply a DC voltage. So this is for a resistance circuit. Then let me increase the voltage level. I'll apply an input voltage of say 0 to 50 volts for the same resistance. So the DC, the type of the source is same, which is DC. And now if you imagine the DC signal for 0 to 50 volts, it is same as the previous case with a change in amplitude. So there will be again a sharp rise in the voltage signal from 0 to 50 volts, and accordingly the amplitude of current will also increase, but maintaining a very sharp rise from 0 to at certain amplitude. Now let me add inductor to that resistance circuit. Okay, let me add inductance to that resistive circuit. Then try to visualize the response of the system, which is nothing but the current developed in the circuit for both the cases. Okay, so I'm not drawing anything and showing anything because we will be studying this again in the future chapter. So then I will explain in detail. So now just try to imagine the scenario and understand what is meant by analysis of dynamic response. That's it. That's what we need. Okay. So now the resistance and inductances are in series and are connected with a DC source. The first case 0 to 5 volt. I mean you are applying a voltage of 5 volts. Okay. So can anyone tell me, one or two students, take your own time. Can anyone tell me what will be the nature of current developed in the circuit? I repeat the question. We have resistance and inductance circuit which are connected to a voltage source of 5 volts DC. And as soon as I switch on the supply, whether the current developed in the circuit will be same as the previous case or is it different? If it is different, then how it is, how it will be. You can explain in words. I'll give 2 minutes of time. You can work out yourself. You have RL circuit and a DC source. Think of yourself.
Current will increase exponentially.
Okay, current will increase exponentially. Any other answer?
To the saturation value after 5 of time.
Okay, there will be a saturation after certain time. One more answer. Current will be constant. Anybody wants to give answer? Anybody else? Okay, that's fine. So let us understand how the current is developed. So if you write the mathematical equations for this circuit, I mean in terms of a differential equation, and if you solve it using either Fourier or Laplace, you will end up with certain expression for I of t. Okay, you'll end up with certain expression for instantaneous current I of t. And if you plot I of t for that particular expression with respect to time, then you will get the current graph or the waveform for the current as gradually increasing and getting settled or saturated after certain time instant. So there will be a gradual increase. Okay, it is not constant or it is not same as that of a resistance case, or it is not exponentially increasing. Exponentially increasing is like a wrong way. So we can say that it is gradually increasing and settling at certain value of time. Okay, Mr. Rahul is message, it's in AC sir, but I have asked for DC brother. Okay, you have to answer only for my question, not for your questions. That's fine. Next, that is dynamic response for RL circuit. So coming back to analysis of dynamic response of RL circuit, what you are going to analyze in that graph? What are the parameters you need to consider in that graph of current? Okay. So I repeat, for those who are facing difficulty, I repeat the question again, like what we are going to do. Now we are analyzing the dynamic response of RL circuit, in which voltage was the input given and current is the output. Okay. So cause and effect scenario. So cause is always input, effect is always output. So what we are going to analyze with I of t? So for that purpose, let us go to second scenario where we have applied 0 to 50 volts. So when you apply 0 to 50 volts DC to the same RL circuit, then if you compare both the responses, that is for 5 volt DC and 50 volt DC, if you compare the nature of graph of the current developed, it almost looks similar except the saturation value or the settled value. Okay, we'll come to that and prove it later. So when you increase the DC voltage, the nature in which the current developed is almost similar to that in 5 volt case. So what happened? What difference you can understand by changing 0 to 5 or 0 to 50? So that is a question mark at. Okay. So to get the answer for that question mark, add one more element, C. C to the same RL circuit. So now it is RLC circuit with a DC voltage given. With a DC voltage given as input. So now you have two circuits, one RL and another RLC, and let us stick to only one voltage source, so 0 to 50 volt or 50 volts of DC, which is connected to both the circuits. So now the question is very simple. Do you expect the same current in both the circuits? I mean, if you plot the graph for I of t, will it be same in both RL and RLC circuit? Obviously no, because you have a capacitance in other circuit. Therefore, there will be a change in the instantaneous values. So what I mean to highlight the word instantaneous frequently is if you start calculating the current values, say from t equal to 0 second, t equal to 0 second onwards, that is say t equal to 0 second, first value, calculate for RL circuit and calculate for RLC circuit, then increase t equals to say 1 millisecond, then 5 millisecond, 10 millisecond, then 50. Like that, if you obtain say at least 10 to 20 values of current for every instant of time, and if you plot the graph for that, both will not be same. There will be a difference. So what we need to understand by analyzing dynamic response is how much time it will take to reach constant value or settling value or saturation value. So this is one important parameter. The time required to reach the saturation. Of course, it will reach to saturation in both the circuits, but in a different fashion or in a different way, we can say. Okay, so that is one such parameter. Then, will there be any oscillations? Will there be any oscillations before reaching to the settling value or constant value? If there exists an oscillation, is it preferable? If not, then to what extent we can minimize those oscillations? Okay, so these are the parameters that we need to be analyzed in a dynamic response. There are of course more than these two parameters, I mean, which are not relevant now. We'll study in detail during the third chapter. So the best example is, suppose imagine we have fixed a spring for the door. I mean, to automatically close it when one opens the door. And if you have fixed with a say spring with a bad spring constant, then that door will oscillate. When someone leaves the room and leaves the door, it will start oscillating. So such oscillations are not preferable. So that we can term as bad dynamic response. So a best spring should close the door smoothly. So that's how our analysis goes further. That's it. Next, coming to performance indices. So performance indices, there are mainly three performance indices, most important. So one is speed. One is speed. So this index of performance measures the fastness of the behavior. So how fast the system will respond or behave. Okay. Then if you take an example of two different objects with two different masses, suppose imagine you have a 100-gram box or a mass block, you have a 100 kg mass block, and if you apply 5 newtons for both, then obviously the speed with which the lesser mass responds is more. Okay, that's how it goes. Nothing much to explain with respect to speed, but accuracy. Accuracy is a very important performance index in control system because its consequences will be different in different scenario. Okay, I repeat again. Accuracy is a very important performance index in control system. It will vary with respect to your applications, and its consequences will also vary with respect to your operations. So one such scenario where the performance index is very important. Suppose you imagine you want to ride the bike from say location X to Y. Okay, location X to Y, or suppose from your home to college. Very simple words. Your home to college, you want to ride your vehicle. So your target is college. Then you'll start your system. You'll apply your controller through your brain. Then while coming to college, will there be any unique path? There may be unique road, but there won't be any unique path. Okay, that everyone follows 100% accurately. Okay, it's not required, right? You can follow the road, but different paths are acceptable. So when you take this scenario, your accuracy can be compromised. Okay, and even when you reach the destination, you can park your vehicle anywhere in the campus. There is no fixed point at all. So an error of say 200 meters plus or minus 200 meters at the destination is very much acceptable. Okay, plus or minus 200 meters, which covers the campus parking lot. I cannot say your accuracy can be plus or minus 2 kilometers. Okay, you cannot reach destination on New BL Road by trying coming to college. That is a very huge error. So some compromisable accuracy. But consider another scenario. You have designed a satellite and you want to make it revolve around Earth. Fine. Just imagine. Okay. You have designed a satellite and you want to make it to revolve around Earth. And you will encounter somewhere in your calculation the term pi. Okay, pi, which usually is approximated as 3.142 something. But when you make a design for say satellite, which involves say rotation of a distance up to, in the range of say lakhs of kilometers, then your calculation should be very accurate. If you make a calculation of just 3.142 and if you launch your satellite only with 3.142, then for every kilometer it will cause 0.000001% of error. I repeat, if you launch your satellite with some calculation by considering pi equal to only 3.142, that is up to 3 decimals after the point, and launch your vehicle, it will create very less error because 3.142 is just an approximation. It is not an exact value of the pi. I hope everyone understands that. Correct? 3.142 is approximation or exact value? Can anyone tell me?
Approximation, sir.
Yes, it is approximation. Fine. There is a big list of values. So if you make calculation for 3.142 and launch satellite, then for every kilometer there will be a small error. And when you travel 1 lakh kilometers, that 0.0001% error will become 1% error, or it will go on increasing and creates a very huge error. Fine. So then the accuracy is a very crucial performance index needs to be considered. Or for example, while launching a missile, if you make miscalculation or if you make your theoretical calculation and dump that on the missile program, so instead of targeting a enemy country, it will target our own country. So accuracy is important. Next, tolerance. Third parameter is tolerance. So just understand the philosophical meaning of tolerance. It is how much error you can tolerate to achieve your goal. Okay, so that's it in simple words. You can apply it to the previous examples. Tolerance is just the limit up to which you can tolerate the error. And next comes the design part. So after analyzing all these things, you need to design to achieve your goal. Okay, so let us not dig much into design part now, as we are not considering now in this semester. So the general meaning of design is, by considering all above parameters, one has to design a proper controller for the system. For example, if your extent of stability is less, you have to increase. If your bike is getting unstable at 100 km per hour, you being a control engineer make some modification and propose that you can ride your bike up to 180 km. So that's where the design comes into picture. So the similar things apply for speed, accuracy, tolerance. So why KTM bikes are more famous? Because the speed of the response is very high. Okay, speed of the response is very high. The design of the system is like that. So design do not mean always designing an algorithm or a controller. It may be a modification in the existing system. So is it clear for everyone? This was a very important slide. It's a very important slide. So we'll move on to the next part quickly. Okay. So the challenges in engineering design are like obtaining the specifications and understanding the complexity of design. Then trade-off. Trade-off is a technical terminology. It is more or less related to with what you can compromise. Okay, with what you can compromise. Do you want to compromise with stability, or you want to compromise with accuracy? Next, design gaps, then risk, then optimize the parameters. So design gaps is fine, you can understand. Risk is also fine, you can understand. Optimize the parameters is a key word. Optimal. Optimal word has a unique meaning. So optimal in the sense, it's not always minimum actually. It's like suppose you have an objective. Your bike should reach from source to destination with a minimum energy consumption, minimum fuel consumption. So if that is your objective, then the design whatever you end up with is called as optimal solution or optimal design. So the word optimal has different meanings in different scenarios. So this is one simplest control system, no need to explain much. So you have a turnable speed control, which is an example for open loop. You have a DC amplifier, you have a DC motor. So battery is operated through amplifier to control the speed, and the respective block diagram is given here. Desired speed you will define yourself. Then that desired speed will be converted into appropriate voltage. So that voltage will be fed to the DC amplifier, then DC motor, then turntable. Somebody had asked me the difference between process and actuator, plant and actuator. So you can clearly see the difference here. Process is table, turntable. Actuator is DC motor. Okay, but when you consider this as a whole system, then DC motor you can term it as a subsystem. So I repeat again, there is a difference between system, process, and plant and actuator. So you can, I have already explained. You can refer anything if you want. So the control device is amplifier. That's it. So this is another example of such system with a closed loop. Let us not go in depth. So this is also done. So speed control system, this was one example. This is quite complicated. Let us skip this part. Then temperature control system. Somebody had given air condition as a closed loop control. The similar thing is being explained here. but the key blocks are A to D converter, interfacing to the computer, then operating the heater through relay. Relay is actuated using amplifier level. So it's how a basic block diagram looks like. Okay, this you can say as a 3D printer or three-dimensional control system. Then this is water level flow regulator. These are very basic and old examples. Okay, so hard disk drive is another example. It is also a kind of control system. And this is one of the multi-input, multi-output, or sorry, multi-input, single output. We can call it as MISO. Example, this is coordinated control system for boiler generator. Let us not look into the operation here. So the basic advantages you might guess very easily now that a good control system will always take care of all these parameters. So this is some theory part, not required. Okay, so final one simple sentence to define the advantages of control system. So the system must be able to yield the correct output even with a disturbance or noise. That's it. Okay. A good control system is the one which will operate or behave properly even with a disturbance or noise. So you ride bike from home to college, even though there is so much of traffic on the road, so many noises, so many disturbances. Fine. So you have a very good control system or a very good brain. And if you get diverted because of disturbance and noise, then I think you will have to check your brain. Okay, the design process goes like this. Okay, this is related to our flow of control system or the study of control system in this semester. So first we need to get the idea of physical parameters in the system and we need to transform them to a mathematical equation. Then you need to convert that to a block diagram to understand the flow of signal. Then you need to create a schematic for that. Then you need to develop a mathematical model for that. Okay. Then the block diagram will be reduced to a simplest level. Then you need to analyze the parameters, then go for the design. So what I mean to say, reduce the block diagram. So we have seen a small block diagrams for every element of the system. So just imagine a scenario. If you draw the block diagrams for the sensors in your body, okay, sensors in your body, then you will end up with n number of blocks. And if you combine all together, it will be a very complex one. So for that reason, you need to reduce the block diagram to understand further or to analyze further. Okay, so this is these are the steps what we are going to do in our study. Okay, there is some typo here. Okay, leave it. Step 1 is to determine the physical system specifications from the requirements. So this first step 1, step 2, step 3 comes in mathematical modeling and block diagram representation. So that almost covers in chapter 1. Then step 4, we will enter to signal flow diagram. That comes in chapter 2. Then step 5, study the closed loop system and its characteristics. That comes in chapter 4, that is root locus. Then the last one is analyze the stability and dynamic behavior and blah 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 to finish the control system. So that's it about the introduction. So I'll wind up today's class with two more simplest videos to understand for you and just one technical paper to give you a brief introduction about what kind of a research goes on. So here is an example. Suppose you want to drive your vehicle from say source to target. So it starts from here, it will take care of speed, then steering angle, it will take care of the acceleration. So it has reached from first to second destination, then from second to third destination. So what goes behind is this program. So this is one such example. Another example. And then here it's an example of say obstacle avoidance. Okay. So this is obstacle, this is your vehicle, and this is the target position. Here it was the initial position. So what goes behind again is a huge mathematics. So what all we have studied in introductory part. Sorry, I think you did not see the video, right? Okay, can see the video now.
Yes,
So
sir.
start position to end position. This is obstacle avoidance example. So there is one program. Yeah. So steering and acceleration are controlled parallel. So a lot of mathematics goes behind this. This is an example of understanding vehicle parking, automatic vehicle parking, and an additional uh, parameter of avoiding the obstacle. Okay. So this was one of such example. Then coming to the last part, yeah, here is one article just to show you like how the flow of research or applications goes in control system. So there is one article I found which is nice and interesting for you people. So it's a tutorial on autonomous vehicle steering controller design, simulation and implementation. Just understand the philosophy of this paper. No need to get into deeper mathematics. So here it covers all the aspects of control system. Controller design, simulation and implementation. So before controller design comes understanding the system itself, which is vehicle here. Okay, there is a vehicle and they have made it as autonomous vehicle. Okay, so this autonomous vehicle has steering controller design. So they have developed a steering controller design, they have simulated and implemented. So just look into the flow. The first step itself is about vehicle model. Okay, so you need to arrive some mathematical definitions for that system. So if you have a mass object and if I ask you to get its mathematical form, you can easily say force equal to mass into acceleration is a mathematical equation related to it. That's meant by vehicle model. Then they have gone to set of diagrams and models. They have got kinematic model and they have written equations related to the model of system. They have ended with a set of equation that defines the kinematic model. Then there comes a dynamic model. Since it is a vehicle, there are two types of modelings. One is kinematic and one is dynamic. But in conventional control system, there is only unique modeling. For the sake of understanding, just go through this. So they have made some modifications, assumptions to reduce the complexity of modeling. And finally, they also have arrived with a model, a set of equations. So this part covers mathematical model of the system. So once they finish off with the mathematical design, then they go ahead with a controller design. So while making controller design, they will define specifications or the objectives themselves. So there may be n number of objectives when you want to design a controller. There is no unique. Okay. So the more parameters, more objectives is also a not good approach. Less objectives is also not a good approach. Optimal objectives are a very good approach. So point to point control objective is one thing they are targeting. Path following is one thing they are targeting. Trajectory following is one thing they are targeting. So trajectory following and path following are different. So we'll understand as we proceed. So with these three objectives, they started a controller design. Okay, so much of calculations, assumptions, minimizations, all those things are done here. Then some graphical representation of how the accelerator and steering angle gains are changed. Okay, then these are some graphical representation of some parameters. So this is one of the example of path following performance simulation. So when they designed the controller, then they simulated it for path following. It looks like this. Then there are some graphical representations, path following graphs. Here it is degree. Okay, here it is tight parking experiment. Okay, it's very much essential in India. So heading angle error and lateral tracking, all these parameters are represented graphically. Okay, so with this, he has finished everything, and before implementation, he has explained some basic concepts, and he has made some calculations for say here GM and PM. You can see here, which we are studying in our control theory. So it is to show about the extent of controllability. Okay, fine. With this, we are winding up the introductory part, and we are concluding the introduction. So that's it. I will